Dear student, as you know, the India and not even India, the entire world is suffering from this virus known as the COVID-19, and all of you are at your home. So this is the best time that we should do something at our home also. We never know when this phase is going to be over. Therefore, in that connection, we, the Department of Physics, have come up with the video lectures, and in this series I'm going to present you the first lectures on the elastic property of the materials. In this unit, we are going to cover the following chapters, or following the topics that include some of the basic definitions of the elastic property of the materials, the Hooke's law, and detailed analysis of a stress and strain curve. So what is elasticity? Elasticity is the branch of the science that deal with the elastic property of materials. What is the deforming force? This is the force that produces the deformation. Deformation include the change in the dimension, which include again the length, volume, shape of the object, etc. Restoring force is the force equal and opposite to the deforming force that come into the play, which tries to restore the body to original state. On the removal of deforming force, restoring force bring the body to its original state. Elasticity or elastic property is a property of the material by virtue of which they regain their original shape and size after the removal of the deforming force or the force which is acting on them. Plasticity or the plastic property is the property of the material by virtue of which after the removal of the force they are not able to regain their shape. Now let us see the classification of the materials. Materials are classified into two groups based on their elastic properties. These are elastic materials, and they are the materials which can regain their state on the removal of the deforming force. Example are the quartz, steel, rubber, etc. Second is the plastic material. They are those materials which are not able to regain their shape on the removal of the deforming force. For example, putty, which is being used in the house decorations, the clay, mud, wax, lead, chewing gums, etc. In general, no material is perfectly elastic or perfectly plastic. You must be knowing that ivory is almost perfectly elastic. So similarly, the atomic collisions are almost perfectly elastic. Now load is the external force acting on the body that produces the change in the dimension of the body. So what is the stress? Stress is the force acting per unit area of the cross section of the wire or load, or stress is the restoring force per unit area of the cross section of the wire or the rod. So stress can be given as the force per unit area. So naturally the unit of the force is Newton, and area we can say meter square. So its unit will be Newton per meter square. Strain is the ratio of the change in the dimension of the material to the original dimension. So dimension includes a length, its a volume, its a width, so etc. So there should be change in the dimension. So what we can say, strain is a change in the dimension to that of the original dimension. So now let's see the type of the strains. So there are three types of the strain, and these can be given as the longitudinal strain. So let's see the figure on this. So as you can see the diagram over here. So here we have taken any rod that has been taken over here. So a tangential force F has been given from both the side. It is being stretched from this side as well as it is being stretched from this side. So its length has increased to the value. Its original length was L, and it has increased by the value of L plus delta L. So naturally, if the length has increased, so naturally the width has got decreased. So let us suppose this original diameter was the D, this is your D, and by when the length has increased, so the dimension has got decreased, and that dimension we are saying D minus delta D. So therefore what we observe here in this case, so while the length is increased, its diameter is getting decreased, and therefore accordingly we'll have the two type of the longitudinal strain. And these two types can be given as. First is your lateral strain, where there is only change in the diameter. So delta D is the change in the diameter upon the original diameter is D. So this is your delta D upon D. This will call as the lateral strain, and throughout this we are going to represent this by the term beta. So beta is equal to delta D by D. The next is coming to your longitudinal strain. So here we have taken the longitudinal strain. So longitudinal strain can be given as the change in the length to that of the original length. So delta L by L is your longitudinal strain, and this longitudinal strain we are going to represent by the term alpha. Okay, so now we are going to take the ratio of the lateral strain to that of the longitudinal strains. So if this we are taking the ratio of these two, then we will be getting a ratio, and this ratio is called the Poisson's ratio. So it is defined as the relation of the lateral strain to that of the longitudinal strain. So therefore what we can say, Poisson's ratio is lateral strain upon longitudinal strain. So lateral strain, as we have seen earlier, delta D by D, and the longitudinal strain is delta L by L. So therefore just we have re-simplified this. So what we can say, this is equal to your delta D into L upon D into delta L. Alright, so now let's come to the another type of this, that is the volume strain. So let us suppose here we have taken a cube. This is a cube that we have taken. On this cube we are putting the force from all the three dimensions. So let us suppose we are putting the force along the x direction, along the y direction, and along the z direction, and the cube is being squeezed. That is, we are trying to compress it. So therefore what is happening, its length is getting decreased, its breadth is getting decreased, and its thickness is getting decreased. So all around its length, breadth, and thickness is getting decreased. So naturally then there is going to be change in the volume. So what we can say, so this strain will be equal to what is the change in the volume. So let us suppose that change in the volume is equal to delta V, and original volume is V. So this will be called as your volume strain. Similarly, we are coming to the another term called the shear strain. Suppose you have taken a book. So just imagine this is the upper part of your book, and you are going to apply a tangential force on the top surface of your book. So what will happen? Your book is going to be sheared. So this book, the top face has traveled this distance delta x. Similarly, it has got traveled another distance delta x on the other side. So what is happening? It has got sheared by this angle theta. So in this process, what is happening? There is a lateral displacement between the two layers, and let us suppose that lateral displacement we are representing it by delta x. And then what was the width of the book? So let us suppose this width of the book was x. So the ratio of this lateral shift between the two layers to that of the thickness of the book, you can say, let us suppose that thickness of the book was x. So these two ratio will be called as shear strain. So therefore what will be the shear strain? Lateral displacement between the two layers upon the perpendicular distance between the two layers. So delta x by x will be called your shear strain. Okay. So now let us come to the another one, which is called the Hooke's law, and here we are going to analyze the detail of it with the stress strain curve. So Hooke's law states that the within elastic limit of that body, so for the different above the body we will have the different limit of the elasticity. So stress varies directly to the strain. So this is the statement that it says that within the elastic limit of a body, stress varies directly to strain. So what we can say, E is equal to stress upon strain. So here we have given the E is your proportionality constant. All right. So now let us see this curve. Let us suppose we have taken any wire, and on that wire we have started loading. We have started loading with the load on this wire, and then what is happening? The wire starts stretching. So let us suppose this is the wire, and on this wire we are putting the load. This is the load that we are putting. So what will happen? So this wire is going to stretch beyond a certain limit. So this is how the wire is going to stretch, right? Now if you are going to take away the force, then this wire will start coming to it will come to its original position, right? So what was the original position? The original position, let us suppose, was x. So it will come to the original position x. Okay. So now what is happening in this case? So let us see this with the stress strain curve. So what we are saying, if you are going to put the load, then wire is getting elongated, and let us suppose by elongation the wire has come from O to A. Now what will happen? Now after this you start deloading the wire, that is weight that you are putting here. So remove those weights. Then what will happen? This wire will come again to the original position O in the same path. That is, as it has gone from, by increasing the weight. Weight is nothing, it's a stress. By increasing the stress, its strain was increasing. So it has gone from O to A, and as we are withdrawing the load, it will be coming back to original position O. So what will this original position call? So let us see. So what we have done, consider a material subjected to a continuously varying load or stress. If we plot a graph of stress along the y-axis and a strain along the x-axis, we get a stress strain curve, and which we have named as O, A, B, C, D, E and G. So you can see in this diagram. So from O to A, as I have explained to you, the stress varies directly to a strain. So as you are going to load this, the wire is getting elongated, and you start deloading, the wire will come exactly following the same path to the original position O. Okay. So what we say, this point A is called, it is going to perfectly obey the Hooke's law, and this is called your perfectly elastic limit. So up to A point, the wire is in the perfectly elastic regions. Now let's go beyond this. Now if the stress is increased, now what we are going to do, from A to B, as you can see, stress is increasing, but there is very slight increase in the strain. So strain is also increasing, and we have come to a point B. You mind it, A and B is very close. So now in this region A, the material is not in the perfectly elastic regions. It is partially in the elastic region and partly in the plastic region. Alright. So what will happen? If you are going to remove the load, that is stress, if it is being removed, the object is not going to come back exactly the same path, that is in the path BO. Rather, it is going to come to the original position in another path, and that path will be equal to BF. So it is going to come back to original position in the path BF. So what has happened? This OF that we can see over here, this OF has permanently got embedded in the system. So in these regions, the body is neither in the perfectly elastic region nor in the perfectly plastic regions. If the stress is removed, the material return to the original position BF along the OF, as I have explained you, and this is called the residual strain acquired by the material, called the permanent set. So this will also call permanent set. This OF will call as permanent set. This OF will be called as permanent set. Alright. Now let's go further, and from B, let's not increase any stress, right? So from B to C, further slightly increase of the stress, the region BC is irregular in shape. Now you can see slightly we have increased the stress, but there is a huge change in the strain between B and C, right? So with slightly increase in the stress, there is a large change in the strain, and that region is a very small region. This region BC is called the yield stress region, right? This B point will be called as the upper yield point, and C will be called as lower yield point. So this is called your yield regions B and C. So sudden increase in the strain gets stopped at C, and this point C is called your lower yield points. Okay, now let's go beyond. If the stress is gradually increased beyond C, then now you can see the stress is being increased, and the stress has reached to a maximum value D, right? So what will this C and D will happen? So here stress is also increasing and strain is also increasing. Stress is taking a peak value at D. So if the stress is gradually increased beyond C, the strain increases and follow the path CD. The region CD is called the plastic region. So from here, the body is not going to regain its original shape. In this region, the thickness of the material decreases without changing the volume, and this is very important, you should remember. In this region, the thickness of the material decreases without changing the volume. The point D is the maximum stress the material can withstand, and the corresponding deforming force is called ultimate or tensile strength, or this is also called strain hardening. That is from point C to D, it is also called strain hardening. Now let's go beyond. In the region DE, as you can see, this is your region DE. So what is happening? The stress is decreasing, but strain is increasing. So in the region DE, strain increases without increase of the stress. In this region, a neck has been formed. That is, wire start getting thinning, and the material breaks even though the stress is decreased. The stress corresponding to the point E is called break stress. The area under the curve OA, B, C, D, E, G, O gives work done per unit volume. So this was your stress and strain curve. Now let us see what are the factors affecting the elastic property of the material. So elastic property of the material are affected by the following factors. So first of all, we are coming to the rolling or hammering. You must be knowing from your childhood, you must have been played with a rod, hammering on them. What happens? So rolling or hammering on the material gradually breaks the bonding in the material, which in turn increase the elastic property of that material. Second is the temperature. If you are increasing the temperature, the material gradually decrease the elasticity. And similarly, impurity, if you are going to add the impurity, so elastic property may increase or it may decrease depending upon what type of the impurity you have added. So the elasticity of the material increases if the elasticity of the impurity is more than that of the material. Similarly, the elasticity of the material decreases if the elasticity of the impurity is less than that of materials. And the last one is annealing. What is the annealing? If you take any material, you gradually heat to a particular temperature, of course less than the melting point, and slowly you cool the material. That is called annealing. What happens because of the annealing? Annealing increases the particle size and material hardens, which in turn reduce the elasticity of the materials. Right? So again, here I have explained the bracket what is the annealing. Alright, for your reference.